Welcome to an introduction on thermodynamics. Today we will be discussing the state postulate and the different types of intensive and specific properties. Let's begin by going over the different types of systems. We have a closed system in which no mass can cross, an open system in which mass can cross, an isolated system where no mass or energy can cross, and an adiabatic system in which no heat can cross. Next, going over the different properties of systems, we have intensive properties, which are independent of mass, extensive properties, which are dependent on mass, and we have specific properties, which are extensive properties that have been made independent of mass. We will examine these a lot closer. Today we're going to talk about specific properties. To exemplify what specific properties are, we're going to start by taking an extensive property, which is dependent on mass, and then making it intensive by making it independent of mass. If we take volume, for example, we can see that when we divide the cylinder in two, its volume and its mass also divide by 2. We want a property that's mass is independent from its volume. For example, when we cut the cylinder in two, its density doesn't change. The density of the original cylinder is the same density as either one of its halves. This is not the case for volume, where if we divide its mass in two, its volume also divides in two. In comes specific volume. We'll see here that the units for specific volume are meters cubed divided by kilograms. In fact, we get specific volume by simply dividing regular volume by the mass. Interestingly, specific volume happens to be the inverse of density. These kind of generalizations don't just apply to volume, but also to other properties that are extensive. For example, enthalpy, entropy, and internal energy are all properties that are dependent on mass. The unit for each of these is kilojoules. One way of thinking about it is that because these units are based in joules, and therefore it's energy, they are dependent on mass. Just think about how conservation of mass is a direct implication of conservation of energy. The solution is simple. We simply take each of these extensive properties, divide it by their mass, and we get their corresponding specific properties. The state postulate says that we need exactly two independent of each other intensive or specific properties. In other words, if we have any two specific or intensive properties, we can solve for all other properties in the system. You might be asking, okay, but what does that mean? Let's say, for example, we have specific volume and pressure. From this, we can determine any one of the following properties: enthalpy, quality, specific entropy, temperature, and internal energy. This actually holds for any two specific properties. Here we have enthalpy and quality, internal energy and temperature. We have to be careful though. What happens if we have pressure and temperature? We assume that we can get all of the rest of the properties, but is this always the case? The answer is no. Pressure and temperature must be independent. When are they independent? Let's take a look at this PT diagram. There's the solid region, the liquid region, and the vapor region. For example, when we're inside the vapor region, we can see that for a given temperature, there are multiple valid pressures. This would make temperature and pressure independent when inside of either the vapor or liquid phase. However, this is not the case when it comes to state changes. During state changes, given a temperature, there is exactly one pressure that corresponds to it. During the change of state, our substance is a saturated mixture. If we want a useful insight from this, we can see that during a state change, pressure and temperature are dependent, meaning that they are not enough to satisfy the state postulate. Any other time, pressure and temperature are independent. A quick example to show the state postulate. So for example, if we have T is equal to 150 degrees Celsius and we have pressure is equal to 300 kilopascals, we want to know, do we have enough information to satisfy the state postulate? We're talking about water, by the way. So we're going to start by checking the saturation water tables in the temperature section, and we're going to see what the saturated pressure is. In this case, it's 475.8 kilopascals. This means that saturated pressure is larger than standard pressure of our problem. This implies that we are dealing with a superheated vapor, And in this case, our properties are independent. This means we do satisfy the state postulate. Thank you for listening to my presentation.